700 million years after everything began, a galaxy the size of our own already existed. By every law we understand, it should not be there. The atoms needed to build it had not yet gathered. The dark matter scaffolding had not yet formed. Yet there it stands in telescope images, massive and impossible, glowing red with the light of billions of ancient stars. We thought we understood how galaxies grew. We were wrong. If you enjoy unraveling cosmic mysteries, hit that like button and subscribe. Prepare yourselves. We begin. In July 2023, astronomers pointed the James Webb Space Telescope toward a patch of seemingly empty space. What came back changed everything we thought we knew about the universe. 6 galaxies appeared in the data. At first glance, they looked like red smudges against the cosmic darkness. Nothing special. But when researchers calculated how far away these objects were, the measurements made no sense. The light from these galaxies had traveled for over 13 billion years. They existed when the universe was barely 500 to 700 million years old. Here's where it gets strange. Each of these galaxies contained more than 10 billion times the mass of our star. One of them matched the entire mass of the Milky Way. Think about that for a moment. Our galaxy spent billions upon billions of years gathering material, merging with smaller galaxies, slowly building its spiral arms and central bulge. These ancient monsters accomplished the same feat in a fraction of that time. Mike Boylan-Colchin, the astronomer who analyzed the data, put it simply: if the masses are correct, we're in uncharted territory. Something fundamental about our understanding is broken. The standard model of cosmology has guided scientists since the late 1990s. It explains how the universe expanded after the Big Bang, how matter clumped together, how galaxies formed over vast stretches of time. It's been tested thousands of times. It works. Except now it doesn't. These 6 galaxies violate the basic math. There simply wasn't enough matter available in that tiny slice of early cosmic history to build structures this massive. According to our best calculations, the atoms needed to construct these galaxies hadn't even finished gathering yet. But the telescopes don't lie. Scientists ran the numbers again and again, checking for errors. The galaxies remained impossible. They sat there in the data like boulders in a river, unmovable, undeniable. If they're real, and every measurement suggests they are, then something very different happened in the early universe than we predicted. Perhaps matter clumped together faster than our equations allow. Perhaps gas turned into stars with impossible efficiency. Perhaps forces we haven't discovered yet were at work, pulling matter together in ways we can't currently explain. The implications stretch far beyond 6 strange galaxies. If these structures formed this quickly, our entire framework for understanding cosmic evolution needs revision. The timeline of the universe's development, the formation of the first stars, the growth of black holes, the emergence of galaxy clusters, all of it might need rethinking. And here's what makes this discovery even more unsettling. These 6 galaxies weren't hiding in some distant corner of the universe. They appeared in a relatively small patch of sky that Webb observed. If 6 exist in one small area, how many more are scattered across the cosmos, quietly defying everything we thought possible? The monster galaxies are just the beginning of the mystery. Galaxies aren't supposed to grow this fast. There's a cosmic speed limit built into the very fabric of reality, and these ancient giants appear to have shattered it. Let's break down why this seems impossible. After the Big Bang, the universe was a hot, dense soup of particles. As it expanded and cooled, atoms formed. Hydrogen first, then helium. These atoms spread out across space, creating thin clouds of gas. Gravity slowly pulled the gas together. Over millions of years, these clouds collapsed into the first stars. Those stars grouped into small clusters. The clusters merged into dwarf galaxies. The dwarf galaxies crashed together to form larger galaxies like ours. This process takes time, enormous amounts of time. Current theories suggest that building a galaxy the size of the Milky Way requires at least several billion years of steady growth. Mergers, collisions, gas accretion, it all adds up slowly, like saving pennies in a jar. But these 6 ancient galaxies completed the entire process in under 700 million years. That's roughly 100 times faster than our models predict. The numbers get worse when you dig deeper. These galaxies didn't just form quickly, they formed efficiently. Astronomers estimate they would need to convert nearly 100% of their available gas into stars. In today's universe, we observe a maximum conversion rate of about 10%. The rest of the gas gets blown away by stellar winds, heated by supernovae, or ejected by growing black holes. Only a small fraction actually condenses into stars. That's normal. That's how physics works. A 100% conversion rate sits right at the edge of theoretical possibility. It would require conditions so perfect, so fine-tuned, that encountering one such galaxy would be extraordinary. Finding 6 in a single observation defies probability. Think of it like trying to boil water with a candle. Sure, technically possible, but now imagine doing it 6 times simultaneously in different rooms, each time achieving perfect efficiency with 0 heat loss. The odds become astronomical. What could cause this extreme efficiency? One possibility involves the early universe itself. Perhaps gas clouds in the infant cosmos were denser, more concentrated. Perhaps the temperature conditions were just right for rapid cooling and collapse. Perhaps gravity worked slightly differently in those first few 100 million years. Or perhaps we're missing something fundamental. The measurements come from the Cosmic Evolution Early Release Science Survey, a multi-institution project led by astronomer Stephen Finkelstein. Multiple teams have examined the data independently. They all arrive at the same disturbing conclusion. These galaxies shouldn't exist, yet they do. The standard cosmological model, lambda-cold dark matter, has successfully explained countless observations for over 2 decades. It predicted the cosmic microwave background's patterns. It explained how galaxy clusters formed. It matched observations of the universe's expansion rate. Scientists trusted it because it kept working. Now it's failing its most crucial test. If galaxies can form this quickly, what else have we gotten wrong about the early universe? Imagine trying to build a skyscraper using every single grain of sand in a desert. No waste, no leftovers, perfect efficiency from start to finish. Now imagine doing that in less than a year. That's essentially what these early galaxies achieved with gas and stars. The problem runs deeper than just speed. It's about the fundamental physics of star formation and why the process is naturally inefficient. When a cloud of gas begins to collapse under its own gravity, it heats up. The atoms inside start moving faster as they get compressed. This creates outward pressure that fights against gravity's inward pull. For stars to form, the gas must cool down enough that gravity wins. In the modern universe, most gas clouds never cool sufficiently. They stay warm and puffed up, resisting collapse. Only the densest, coldest pockets manage to condense into stars. The rest gets blown away or remains floating in space. Massive stars make this worse. Once they ignite, they pump out intense radiation and powerful winds. This energy heats the surrounding gas, preventing new stars from forming nearby. When these giants die in supernova explosions, they blast remaining gas clear out of the galaxy. It's a self-limiting process. Star formation naturally puts the brakes on itself. That's why today's galaxies convert only about 10% of their gas into stars over billions of years. The rest escapes. For the ancient galaxies to reach their observed masses so quickly, they would need to bypass all these limiting factors. Every gas cloud would need to collapse. Every atom would need to end up in a star. Zero waste, zero loss. Researchers have run computer simulations trying to recreate these conditions. The models refuse to cooperate. Even when scientists artificially boost the efficiency parameters, the simulations can't produce galaxies this massive, this quickly. The physics simply doesn't allow it, unless the physics was different back then. What if the early universe had properties we don't account for? What if the first gas clouds were fundamentally different from the ones we observe today? Modern gas contains traces of heavier elements, carbon, oxygen, iron, forged in previous generations of stars. These elements help gas clouds cool and fragment. But the first clouds had none of these elements. They were pure hydrogen and helium. This should have made star formation harder, not easier. Pure hydrogen doesn't cool as efficiently as contaminated gas. Yet somehow, these galaxies thrived. Another possibility involves dark matter, the invisible substance that makes up most of the universe's mass. Dark matter creates gravitational wells where normal matter collects. Perhaps in the early universe, dark matter clumped together more tightly than our models predict, creating deeper wells that trapped gas more effectively. Or perhaps the answer involves something we haven't even considered yet: new physics, unknown forces, processes that don't operate in the modern cosmos but dominated the ancient one. The gas conversion problem isn't just a puzzle for astrophysicists. It challenges our understanding of chemistry, thermodynamics, and gravity itself. If we can't explain how these galaxies formed their stars, we can't claim to understand star formation at all. And star formation is the process that created every element in your body. Every galaxy needs a skeleton, something to hold it together, something to provide the gravitational scaffolding that allows normal matter to collect and form stars. That skeleton is dark matter. Dark matter makes up roughly 85% of all matter in the universe. We can't see it directly. It doesn't emit light or interact with normal matter except through gravity. But its effects are undeniable. It bends light from distant galaxies. It holds galaxy clusters together. It shapes the large-scale structure of the cosmos. According to every model of galaxy formation, dark matter came first. In the early universe, tiny fluctuations in dark matter density grew under gravity's influence. These dense patches attracted more dark matter, forming larger clumps. Over millions of years, these clumps became halos, massive spheres of dark matter suspended in space. Normal matter fell into these halos, drawn by their gravity. The gas inside the halos cooled and condensed, stars ignited, galaxies were born. This process, called hierarchical formation, explains the modern universe beautifully. Small halos merge to form larger ones. Dwarf galaxies combine into spirals. Spirals crash together to create ellipticals. It's cosmic assembly from the bottom up, but hierarchical formation requires time. Dark matter halos don't spring into existence overnight. They grow gradually, pulling in material from their surroundings. Small halos form first, within a few 100 million years after the Big Bang. Larger halos take longer. A halo massive enough to host a Milky Way-sized galaxy needs at least 1 to 2 billion years to fully develop. The ancient monster galaxies appeared at 700 million years. Their dark matter halos hadn't had enough time to form. Claudia Lagos, an astronomer studying these objects, described the situation clearly. Massive dark matter structures necessary for holding early galaxies together did not yet have time to form this early in the universe. It's like discovering a fully grown oak tree in a field that was bare dirt yesterday. The tree needs soil to anchor its roots, but the soil itself needs time to form. If you find the tree before the soil exists, something extraordinary has occurred. Scientists have considered several explanations. Perhaps dark matter clumps together faster than current theories predict. Perhaps the early universe had regions where dark matter was already concentrated, jump-starting the formation process. Perhaps gravity worked slightly stronger in the past. Each possibility requires modifying fundamental physics. Some researchers have proposed that dark matter might not be cold, as currently assumed. Cold, dark matter moves slowly, forming structures gradually. But if dark matter is warm or fuzzy, moving faster or behaving quantum mechanically, it could create different patterns. Simulations show that fuzzy dark matter forms elongated filaments instead of spherical halos. Galaxies born in these filaments might grow differently. However, changing the properties of dark matter affects everything else. It alters predictions about the cosmic microwave background. It changes how galaxy clusters should look. It modifies the universe's expansion history. Any modification needs to match countless other observations, not just these 6 galaxies. So far, no modification works perfectly. The alternative is more unsettling. Perhaps these galaxies formed through a process we haven't discovered yet. Perhaps in the earliest moments of the universe, before the standard rules fully applied, matter and dark matter interacted in ways we don't understand. Whatever the answer, it forces a confrontation with our ignorance. We thought we understood dark matter's role in cosmic evolution. These galaxies suggest we barely scratched the surface. In the infant universe, barely 700 million years after creation, astronomers found something that shouldn't exist for billions of years: a galaxy graveyard. The galaxy has a designation RUBIESUDSQGZ7. Names in astronomy aren't poetic, but what this object represents sends chills through the scientific community. It's dead, completely dead. When astronomers say a galaxy is dead, they mean it stopped forming stars. Star birth requires cold gas. Without fresh gas inflow, the fuel runs out. The galaxy goes dark. The massive hot blue stars burn out first. Only small, cool red stars remain, giving the galaxy a distinctive red color. No new light, no new growth, just slow decay as the remaining stars age. This process takes time in the modern universe. A galaxy needs billions of years to consume its gas, form its stars, and finally exhaust its fuel. Dead galaxies are common around us because our cosmic neighborhood is ancient. These galaxies had time to live full lives before dying. RUBIESUDSQGZ7 never got that chance. This ancient galaxy formed over 10 billion solar masses worth of stars in less than 600 million years after the Big Bang. Then it stopped. Star formation shut down completely within 50 to 100 million years of observation. The galaxy blazed bright, then went silent while the universe was still in its infancy. Andrea Weibel, the researcher who analyzed the galaxy's spectrum, explained the significance. Models and simulations contain very few such objects, more than 100 times fewer than this discovery suggests should exist. Finding one dead galaxy this early challenges theory, but Webb hasn't found just one. Multiple quiescent galaxies have appeared in the telescope's data, scattered across the early universe, some at 1.2 billion years after the Big Bang, others even earlier. The pattern suggests something systematic, not random. Whatever process kills these galaxies operates efficiently in the early universe, far more efficiently than in the present day. What could shut down star formation so abruptly? In modern galaxies, several mechanisms can stop star formation. Supermassive black holes at galactic centers can heat surrounding gas, preventing it from cooling and collapsing. Massive star winds can blow gas out of the galaxy entirely. Mergers with other galaxies can disrupt the delicate balance needed for star formation. Environmental effects in galaxy clusters can strip gas away, but these mechanisms work slowly, taking hundreds of millions of years. RUBIESUDSQGZ7 shut down in a cosmic instant. The galaxy appears compact in Webb's images. It may have formed through a rapid collapse, where gas fell inward quickly and converted to stars in multiple bursts. This intense activity would have been spectacular while it lasted. Billions upon billions of stars igniting within a small volume. The energy output would have been staggering. Perhaps that very intensity killed it. The concentrated star formation might have generated feedback powerful enough to blow away all remaining gas in one catastrophic purge, like a fire consuming all available fuel so quickly it extinguishes itself. Or perhaps a supermassive black hole formed early in the galaxy's center. As matter fell into the black hole, it would heat to millions of degrees, emitting intense radiation. This radiation would push against infalling gas, creating winds strong enough to clear the entire galaxy. Either way, something violent happened, something final. The discovery forces a troubling question. How many other dead galaxies are hidden in the early universe, too faint for even Webb to detect? Astronomers started calling them little red dots. The nickname sounds almost cute, until you realize what they represent: objects that defy classification. When Webb's images first came back, scattered among the ancient galaxies were tiny red points, smaller than the monster galaxies, fainter but numerous. Dozens of them appeared in every deep field observation. Their color told a story. Red light from distant objects indicates age and distance. Light from the early universe gets stretched by cosmic expansion, shifting toward the red end of the spectrum. The redder the object, the farther away and older it is. But these dots looked different from normal galaxies. They were too compact, too bright for their size. Their light had unusual properties that didn't match typical galactic spectra. At first, researchers assumed they were seeing more dead galaxies like RUBIE SUD SQGZ7. The red color matched. The timing matched. Everything suggested these were scattered examples of early quiescent galaxies, galaxies that had stopped forming stars. Then, the spectroscopy results came back. Spectroscopy splits light into its component wavelengths, revealing what elements exist in the object and how they're moving. It's like taking a cosmic fingerprint. When scientists analyzed the little red dots closely, many showed emission lines, bright spikes at specific wavelengths, indicating hot, glowing gas. Dead galaxies shouldn't have glowing gas. They should be dark except for the faint light from old stars. Something else was powering these objects. Many of the little red dots showed signatures of active galactic nuclei, supermassive black holes actively consuming matter. When material spirals into a black hole, friction heats it to extreme temperatures. The hot gas glows brilliantly across the spectrum. This process can outshine all the stars in a galaxy combined, which means at least some of the little red dots aren't galaxies at all. They're black holes in disguise. But here's where it gets complicated. Not all little red dots show black hole signatures. Some look genuinely dead. Some show mixed signals, partly stars, partly black hole. Each one seems to tell a different story. The light from black holes can trick measurements in significant ways. If a little red dot's brightness comes mostly from a growing black hole rather than stars, the galaxy appears more massive than it actually is. Researchers might think they're seeing a monster galaxy when they're really observing a relatively small galaxy hosting an enormously active black hole. This could resolve some of the tension with cosmological models. If many of the impossible galaxies are actually black hole-dominated systems, their true stellar masses might be much lower than initial estimates suggested. The crisis in cosmology might partially ease, but it wouldn't disappear entirely. Even accounting for black hole contamination, too many massive objects exist in the early universe. The standard model still faces challenges, and the black hole explanation creates its own problems. How did supermassive black holes form so early? Current theories suggest these giants need millions of years to grow from stellar mass seeds. Finding them already massive just a few 100 million years after the Big Bang implies they grew impossibly fast, or they formed through a process we don't understand. Some scientists have proposed that primordial black holes, formed directly from density fluctuations in the moments after the Big Bang, might explain the early supermassive black holes. These wouldn't need to grow from stellar remnants. They could start huge. The little red dots refuse to reveal their secrets easily. Each new observation raises more questions than it answers. The debate splitting the astronomical community comes down to a fundamental question. What's actually glowing inside these early galaxies? On one side, researchers argue that the mass measurements are essentially correct. These are genuinely massive galaxies, packed with billions of stars, formed impossibly quickly. If true, cosmology needs major revisions. On the other side, scientists contend that supermassive black holes are responsible for much of the observed brightness. the galaxies themselves might be smaller and less problematic. If true, the crisis softens but doesn't disappear. Both camps have evidence. Neither can prove their case conclusively yet. The black hole hypothesis has clear advantages. We know supermassive black holes can generate incredible luminosity. A black hole consuming matter produces light across the entire electromagnetic spectrum. This light can mimic or overwhelm the light from stars. Observations from Earth, looking back 13 billion years, might struggle to separate the two sources. Friction in the swirling accretion disk around a black hole heats gas to millions of degrees. At these temperatures, the gas emits X-rays, ultraviolet light, and intense visible light. This creates emission lines in the spectrum, bright spikes at specific wavelengths corresponding to particular elements. Many early galaxies show exactly these emission lines: hydrogen alpha, oxygen 3, signatures consistent with hot gas around active black holes. Stephen Finkelstein, who leads the survey that discovered many of these objects, supports this interpretation. His team's analysis suggests black holes contribute significantly to the light from many early systems. When you subtract the black hole contribution, the remaining stellar masses become more reasonable. The standard model of cosmology still holds, but the evidence isn't universally convincing. Some of the massive early galaxies show weak or absent emission lines. Their spectra look genuinely stellar, dominated by light from large populations of stars. These objects seem harder to explain away with black holes. Additionally, the sheer number of active supermassive black holes required creates its own puzzle. Black holes need to grow. The leading theory suggests they start as stellar remnants collapsed, cores of massive stars, weighing perhaps tens of times more than our star. To reach supermassive status, containing millions or billions of solar masses, they must consume enormous amounts of matter. This growth process has limits. As matter falls toward a black hole, it heats up and radiates energy. This radiation creates pressure that pushes against infalling matter, limiting how fast the black hole can grow. The limit, called the Eddington rate, restricts growth to doubling the black hole's mass roughly every 50 million years. Starting from a stellar mass seed and growing at the maximum Eddington rate, a black hole needs about 1 billion years to reach supermassive status. But we're finding supermassive black holes or objects that appear to host them at 700 million years. The timeline doesn't quite work, unless the seeds were bigger to start with, or the Eddington limit doesn't always apply, or black holes grew through super-Eddington accretion in brief, intense bursts. Each explanation requires special circumstances. Emma Curtis Lake, an astronomer studying these objects, summarized the situation. There's not a tension with cosmology from black holes, just new physics to be understood about how they form and grow so rapidly. The distinction matters. If it's a cosmology crisis, we need to rethink the fundamental structure of the universe. If it's a black hole formation crisis, we need to understand extreme physics in extreme conditions. Either way, something profound escapes our current knowledge. For over 2 decades, one framework has guided our understanding of the cosmos. It's called lambda cold dark matter, or LCDM for short. Scientists developed it in the late 1990s, refining it through countless observations and experiments. The model works beautifully. It explains the cosmic microwave background, the faint afterglow of the Big Bang still visible today. It predicts how galaxies cluster across billions of light years. It accounts for the universe's accelerating expansion. Test after test, LCDM passed with impressive accuracy. Until now, the model rests on several key assumptions. First, that dark matter is cold, meaning it moves slowly relative to the speed of light. Cold, dark matter forms structures gradually, starting small and growing through mergers over billions of years. This bottom-up process matches what we observe in the local universe. Second, dark energy drives cosmic expansion. This mysterious force, represented by the lambda in LCDM, causes space itself to stretch. It explains why distant galaxies are racing away from us at accelerating speeds. Third, normal matter atoms. The stuff we're made of makes up less than 5% of the universe's total mass energy. Dark matter dominates, providing the gravitational framework. Dark energy dominates even more, controlling the expansion. Within this framework, predictions emerge. Computer simulations using LCDM parameters can calculate when the first stars ignited, when galaxies started forming, how massive early galaxies could be. These predictions have matched observations remarkably well until Webb looked deeper. The massive early galaxies violate LCDM's most fundamental prediction: how much matter should be available for star formation in the early universe. The model calculates that only a tiny fraction of atoms should have collected into galaxies by 700 million years post-Big Bang. Most matter should still be scattered diffusely through space. The 6 monster galaxies contain far too much mass. According to LCDM, gathering that much matter into compact structures that early should be extraordinarily rare, so rare we shouldn't see any in Webb's relatively small survey area. Yet there they are, 6 in one small patch of sky. If the survey area is representative, the entire early universe must contain thousands upon thousands of these impossible objects. Boylan-Kolchin's analysis put precise numbers on the problem. Based on LCDM predictions, these galaxies should be using up a larger fraction of available atoms than the model allows. Instead of the typical 10%, they appear to have converted 100% of available atoms into stars. Several escape routes exist, but none are satisfying. Perhaps the masses are overestimated. Perhaps black holes are contaminating the measurements. Perhaps dust is making the galaxies appear farther away than they actually are. Each possibility offers hope that the observations might align with LCDM after further study. But what if they don't? What if after all the checks and corrections, these galaxies remain massive and ancient and impossible? Then LCDM requires modification, not abandonment. The model works too well in too many other contexts, but revision, additions, new physics layered onto the existing framework. One proposed modification involves early dark energy. Perhaps in the universe's first few 100 million years, an additional form of energy existed that accelerated structure formation. This energy would have helped matter clump together faster than LCDM predicts. Then it disappeared, leaving no trace in the modern universe except these ancient massive galaxies. Another possibility involves new forces or particles active only at extreme energies. The early universe was far hotter and denser than today. Perhaps physics operates differently under those conditions, allowing rapid galaxy formation through mechanisms that no longer function. These aren't random speculations. They're testable hypotheses. Future observations should reveal whether these modifications better match reality than standard LCDM. Science progresses by breaking models, then building better ones. 700 million years after the universe began, a galaxy formed, lived, and died. The entire life cycle: birth, growth, death, compressed into a cosmic heartbeat. RUB, IE, SUD, SQGZ. 7 represents the most extreme example of rapid evolution yet discovered. Let's trace its brief, violent history. In the beginning, dark matter and normal matter fell together into a dense clump. The normal matter, mostly hydrogen and helium gas, heated as it compressed. But somehow, despite the heat, the gas cooled rapidly enough to collapse further. Stars began forming, not a gentle trickle of star formation, an explosion. Within a few 100 million years, perhaps much less, this galaxy converted 10 billion solar masses of gas into stars. That's roughly 15 times the mass contained in all stars currently forming in the Milky Way, concentrated into a much smaller volume, blazing with the combined light of billions of newborn giants. The galaxy would have been spectacular. If human eyes could have witnessed it, the night sky would have glowed with countless massive blue stars. Supernovae would have detonated constantly, their shock waves tearing through interstellar gas. The core would have been so crowded that stellar collisions and gravitational interactions between stars would have been common. This intensity couldn't last. Physics wouldn't allow it. Massive stars live fast and die young. The most massive ones burn through their fuel in just a few million years. As they died, their supernova explosions would have blasted away surrounding gas. The radiation from millions of hot young stars would have heated remaining gas, preventing it from cooling enough to form new stars. Or perhaps a supermassive black hole formed early in the galaxy's center. As it consumed matter, the incredible energy released would have created powerful winds. These winds, moving at thousands of miles per second, would have swept through the galaxy like a cosmic broom, pushing gas out into intergalactic space. Within 50 to 100 million years after its formation peak, star formation ceased. The galaxy went quiet. The massive blue stars died. The smaller, cooler red stars remained, but they produce far less light. The galaxy faded from brilliant blue-white to dim red. Pascal Loesch, a researcher studying this object, emphasized its importance. Finding the first examples of massive quiescent galaxies in the early universe is critical as it sheds light on possible formation mechanisms. The galaxy's spectrum provides the evidence. When light passes through a prism or diffraction grating, it spreads into a rainbow. Different elements absorb or emit light at specific wavelengths, creating a unique pattern. This pattern is a galaxy's fingerprint. RUBIESUDSQGZ7's spectrum shows a deep Balmer break, a sharp drop in light intensity at a specific wavelength. This break appears when a galaxy's light is dominated by old stars. Young galaxies don't show it. Active star-forming galaxies don't show it. Only dead galaxies display this telltale signature. The spectrum also shows absorption lines from calcium and hydrogen. These elements exist in stellar atmospheres. Their presence, combined with the lack of emission lines from hot gas, confirms that stars stopped forming long ago. 13 billion years later, Webb captured the light from this ancient corpse. By now, if the galaxy survived, it would be even older and fainter. It might have merged with other galaxies. It might host a massive elliptical galaxy similar to those we see in today's universe. Or it might have been torn apart by gravitational interactions. We'll never know its ultimate fate. We see only this single snapshot, frozen in time, showing a galaxy that should not exist. Yet it does. What if the universe didn't expand the way we think it did? This question has started circulating through physics departments worldwide. If the early universe expanded faster than our models predict, it might explain the impossible galaxies. But changing the expansion rate means rewriting fundamental cosmic history. Here's why expansion matters for galaxy formation. After the Big Bang, space itself stretched. As it stretched, matter spread out. Dense regions became less dense. Hot gas cooled. The expansion fought against gravity's attempts to pull matter together. This competition between expansion and gravitational collapse determined when and how structures could form. Our current expansion model comes from decades of careful observation. Scientists measure how fast distant galaxies are moving away from us. They study the cosmic microwave background's tiny temperature variations. They track how supernovae brighten and fade at different distances. All these measurements converge on a consistent expansion history. Or so we thought. If the universe expanded significantly faster in its first few 100 million years than we calculate, it would have several effects. Faster expansion would spread matter out more quickly, but it would also mean the universe was denser earlier than we thought because it had less time to dilute itself before reaching a given size. This higher early density could allow matter to clump together faster. Regions that were marginally dense enough to collapse would become strongly dense. Dark matter halos would form earlier. Gas would fall into these halos more readily. Star formation could begin sooner and proceed more rapidly. The massive early galaxies might not be impossible after all. They might just reflect an expansion history we mismeasured. But changing the expansion rate isn't simple. It requires adding new physics to our models. Boylan-Kolchin suggested one extreme possibility: new forces and particles active shortly after the Big Bang. In the Standard Model, 4 fundamental forces govern the universe: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. We've tested these forces extensively. They work. But perhaps a 5th force existed briefly in the early universe, then vanished as conditions changed. This isn't as wild as it sounds. Physics already includes examples of forces that appear and disappear depending on conditions. At extremely high energies, the electromagnetic force and weak nuclear force merge into a single electroweak force. Perhaps at even higher energies, present only in the first moments after the Big Bang, additional forces activate. A new force could affect how dark matter clumps. It could change how normal matter interacts with dark matter. It could accelerate structure formation in ways gravity alone cannot achieve. As the universe cooled and expanded, this force might have weakened or disappeared entirely, leaving no trace in the modern cosmos except those ancient massive galaxies. Alternatively, new particles might provide the answer. Particle physics already includes particles that exist only at high energies. The Higgs boson, discovered in 2012, requires enormous energy to create and decays almost instantly. Perhaps the early universe hosted other particles, now gone, that influenced cosmic evolution. These particles could have served as additional dark matter, making halos form faster. They could have generated pressure that compressed gas into stars more efficiently. They could have carried energy and momentum in ways that altered how structures grew. Testing these ideas is extraordinarily difficult. We can't recreate Big Bang conditions in laboratories. We can't observe the first few 100 million years directly. We can only look at the consequences, the galaxies that survive to the present day, and work backward to infer what must have happened. Webb provides the consequences. Now theorists must figure out the causes. Every particle in your body formed in a star billions of years ago. Every force holding those particles together has existed since the beginning. Or has it? The discovery of massive early galaxies forces us to consider whether the universe's first moments operated under different rules than we observe today. Perhaps forces and particles existed then that no longer exist now. This isn't science fiction. It's a logical possibility grounded in established physics. Consider temperature. Heat a metal and it glows red, then white. Cool it down and it becomes solid, then brittle. The same material behaves completely differently depending on temperature. Physics has phase transitions where properties change dramatically. The early universe was incomprehensibly hot. In the first trillionth of a second, temperatures exceeded 10 trillion degrees. Under these conditions, particles and forces we've never encountered might have been commonplace. As the universe expanded and cooled, these exotic phenomena would have disappeared. Like steam condensing to water, then freezing to ice, the fabric of reality shifted through phases. What was possible at one temperature became impossible at another. Modern particle accelerators can recreate some of these early conditions. At CERN's Large Hadron Collider, protons smash together at nearly light speed, briefly generating temperatures not seen since microseconds after the Big Bang. These collisions reveal particles that exist only momentarily before decaying. The Higgs boson is the most famous example. It exists for less than a trillionth of a second before transforming into other particles. Yet it plays a crucial role in giving other particles mass. Without the Higgs field permeating space, electrons, quarks, and other fundamental particles would be massless, and the universe would look completely different. What other particles might have existed in the early universe but left no direct trace? One candidate is called the axion. Proposed decades ago to solve problems in particle physics, axions would be extremely light and weakly interacting. If they exist, they could form a component of dark matter. But they might also have been far more abundant in the early universe. when temperatures allowed them to form easily. As the universe cooled, most would have decayed or diluted away, leaving only a small remnant. During their brief dominance, axions could have influenced how matter clumped together. They could have seeded structure formation in ways that pure, cold, dark matter cannot. Simulations, including axions, show different patterns of galaxy formation than standard models predict. Another possibility involves primordial black holes. Unlike black holes formed from dying stars, primordial black holes would have formed directly from density fluctuations in the first moments after the Big Bang. They could have any mass from microscopic to millions of solar masses. If primordial black holes are common, they could serve as seeds for galaxy formation. Their gravity would attract dark matter and normal matter more effectively than diffuse dark matter halos. Galaxies could form around these seeds much faster than hierarchical models predict. Some physicists have suggested modifications to gravity itself. Einstein's general relativity has passed every test in the modern universe. But perhaps at extremely high densities or early times, additional terms in the gravitational equations become important. These terms would be negligible today but significant in the early universe, potentially accelerating structure formation. Each of these ideas, new particles, primordial black holes, modified gravity, makes specific predictions. They affect not just galaxy formation but also the cosmic microwave background, the abundance of light elements, and the universe's expansion history. Testing them requires comparing predictions against multiple independent observations. So far, none perfectly explain the massive early galaxies while maintaining agreement with all other data. The search continues for a framework that works. 1 is an anomaly, 6 is a pattern, hundreds is a crisis. The number of massive quiescent galaxies found in the early universe exceeds theoretical predictions by a factor of roughly 100. Not 10% more, not twice as many, 100 times more. This isn't a minor discrepancy. This is a fundamental breakdown of prediction. Let's understand what 100 times means in practice. Computer simulations model galaxy formation by following billions of particles through cosmic history. Scientists input the laws of physics, the properties of dark matter, the behavior of gas, and the intensity of feedback processes. Then they run the simulation forward, watching virtual galaxies form, grow, and evolve. These simulations have become increasingly sophisticated. They include star formation, supernova explosions, black hole growth, gas heating and cooling, galaxy mergers, and gravitational interactions. Modern simulations reproduce many features of the real universe with impressive accuracy, except early quiescent galaxies. When simulations run forward to 700 million years after the Big Bang, they do occasionally produce massive galaxies that stop forming stars. These are rare events, occurring perhaps once in a large simulation volume. Finding 1 or 2 in a survey would be expected. Finding dozens was not. Andrea Weibel's analysis of RUBIESUDSQGZ7 emphasized this point. Models and simulations contain very few such objects, more than 100 times fewer than the existence of this galaxy suggests. If every observation of 100 early quiescent galaxies matches what simulations predict we should find one, something is desperately wrong with the simulations, or with our understanding of the underlying physics they attempt to model. 3 possibilities exist. First, the observations might be wrong. Perhaps many apparent early quiescent galaxies are actually something else: dusty, star-forming galaxies, active galactic nuclei, foreground objects mistaken for distant ones. This would reduce the discrepancy, but spectroscopic confirmation keeps coming back positive. The galaxies appear genuinely quiescent and genuinely ancient. The observation error explanation looks increasingly unlikely. Second, the simulations might be missing important physics. Perhaps feedback processes in the early universe were dramatically different than today. Perhaps black holes grew faster and shut down star formation more efficiently. Perhaps galaxy mergers happened at rates the simulations don't capture. Adding these missing processes to simulations could increase the predicted number of early quiescent galaxies, but it needs to increase the number 100-fold without breaking anything else. The simulations already match many other observations. Any changes must preserve those successes while fixing this particular failure. That's a narrow target to hit. Third, the cosmological model itself might need revision. If the universe had more matter available for galaxy formation, or if structures formed through a fundamentally different process, the simulations based on current cosmology would naturally fail. This is the most radical possibility. It means LCDM, the framework that has guided cosmology for decades, contains a flaw serious enough to produce 100-fold errors in specific predictions. Scientists are exploring all three possibilities simultaneously. Observers are gathering more data, checking measurements, hunting for sources of error. Simulators are experimenting with new physics, testing whether modified feedback or different initial conditions can boost the number of early quiescent galaxies. Theorists are proposing modifications to fundamental cosmology. The 100 times problem won't vanish with small corrections. It demands a substantial shift in understanding, whether that shift occurs in observational techniques, simulation methods, or theoretical frameworks. One way or another, the universe is trying to tell us something important. Everything hinges on the follow-up observations. The initial discoveries were exciting, but they came from photometry, measuring how bright objects appear in different wavelength bands. Photometry provides quick surveys of large areas but limited detail. Spectroscopy delivers the truth. When light passes through a spectroscope, it splits into its component wavelengths, revealing detailed information invisible to photometry alone. Each chemical element leaves a unique signature. Hydrogen absorbs light at specific wavelengths. So does helium, oxygen, carbon, iron. By reading these signatures, astronomers can determine an object's composition, temperature, motion, and distance. The James Webb Space Telescope carries the most sophisticated spectrograph ever sent to space, near-spec, or near-infrared spectrograph. It can capture spectra from hundreds of objects simultaneously, providing the evidence needed to confirm or refute initial photometric measurements. The verdict has started arriving, and it's complicated. Some early galaxies passed spectroscopy with flying colors. Their spectra show exactly what massive, mature, quiescent galaxies should display. Deep Balmer breaks, indicating old stellar populations. Absorption lines from elements forged in stellar cores. No emission lines from active star formation. These objects are confirmed as ancient giants. RUBIESUDSQGZ7 is the prime example. Its spectrum leaves no doubt. This galaxy formed rapidly, lived briefly, and died young, just as photometric measurements suggested. But other objects revealed surprises. Many of the little red dots assumed to be small dead galaxies turned out to host actively feeding supermassive black holes. Their spectra show broad emission lines, a telltale signature of gas swirling around a black hole at tremendous speeds. The light these objects emit comes substantially from the black hole's accretion disk, not from stars. This discovery significantly impacts mass estimates. If half the light comes from the black hole rather than stars, the galaxy contains half as much stellar mass as originally calculated. The crisis with cosmological models partially eases. Stephen Finkelstein's team published results showing this effect in action. When they carefully separated black hole light from stellar light in early galaxies, many of the apparent monsters shrunk to more reasonable sizes. Not small, but no longer impossibly massive. The standard model of cosmology survived this test. Finkelstein stated it clearly: there is no crisis in terms of the standard model of cosmology. However, the problem didn't disappear entirely. Even after accounting for black hole contamination, roughly twice as many massive galaxies exist in the early universe as LCDM predicts. Not 100 times too many, which would be catastrophic, but twice as many still demands explanation. Why twice? One possibility involves star formation efficiency. Perhaps galaxies in the early universe were genuinely better at converting gas into stars. Not the 100% efficiency initially feared, but perhaps 20 to 30% instead of 10. That modest improvement could account for the remaining excess of massive galaxies. Another possibility involves measurement uncertainties. Determining a galaxy's mass from its light requires assumptions about what types of stars it contains. Different stellar populations produce different amounts of light per unit mass. If early galaxies had unusual stellar populations, perhaps more massive stars than modern galaxies, the mass estimates could be systematically high. Spectroscopy helps resolve these ambiguities. By measuring specific absorption and emission lines, astronomers can constrain the stellar populations more accurately. Each new spectrum refines the picture. The data collection continues. Webb is systematically observing thousands of early galaxies, building a comprehensive dataset that will eventually answer these questions definitively. But spectroscopy is slow. Each observation requires hours of telescope time. Priorities must be balanced. The most interesting targets get observed first, and with every new spectrum, the picture shifts slightly. What seems certain today might look different tomorrow. Light can lie, or at least, it can mislead us spectacularly when we're looking across billions of light years at objects we've never directly sampled. The brightness illusion represents one of the most promising ways to reconcile observations with theory. If the early galaxies aren't as massive as they appear, the cosmological crisis softens significantly. Here's the problem. We estimate galaxy masses primarily from their light. More light generally means more stars, which means more mass. This relationship works well for nearby galaxies, where we can resolve individual stars and measure their properties directly. For distant galaxies, we see only integrated light, the combined glow of billions of stars smeared together into a single point. We must infer the stellar population from this limited information. The inference depends on models of how different types of stars contribute to the total light. Supermassive black holes disrupt this inference dramatically. When a black hole feeds, matter spiraling inward heats to millions of degrees. At these extreme temperatures, the gas emits intensely across the electromagnetic spectrum. A single actively feeding black hole can outshine all the stars in its host galaxy combined. If you're measuring galaxy brightness from across the universe and can't separate black hole light from stellar light, you'll overestimate the stellar mass. You might think you're seeing a galaxy with 1 trillion solar masses, when actually you're seeing a galaxy with 100 billion solar masses plus an incredibly bright black hole. This is exactly what researchers suspect happened with many early massive galaxies. Katherine Swarovski, an astronomer who studied these objects in detail, found that black holes rapidly consuming gas can emit enough heat and light to make their host galaxies appear far brighter and bigger than they actually are. Her team's spectroscopic analysis revealed black hole signatures in many of the supposed monster galaxies. When they subtracted the black hole contribution from the total light, the remaining stellar masses dropped to more reasonable values. The galaxies were still large for their age, but no longer impossibly so. This finding relieves some tension with cosmological models. If most of the extreme outliers are actually black hole-dominated systems, LCDM doesn't face an existential crisis. It faces a smaller problem. Why are there twice as many massive galaxies as predicted, rather than 100 times too many? Twice as many is puzzling. 100 times too many would have been catastrophic. However, the brightness illusion explanation has limits. Not every early massive galaxy shows strong black hole signatures. Some appear to be genuinely stellar-dominated. Their spectra lack the broad emission lines and high-energy radiation characteristic of active galactic nuclei. These clean stellar systems still challenge theory. Even if they're less common than initially thought, their mere existence requires explanation. Additionally, the black hole explanation raises its own questions. How did supermassive black holes grow so large so quickly? A black hole containing 1 billion solar masses, actively outshining its host galaxy, must have grown from something. Current models suggest such growth takes at least several 100 million years, often longer. Finding these giant black holes at 700 million years post-Big Bang implies they formed rapidly, perhaps from massive seeds rather than stellar remnants, or perhaps through superfast accretion that exceeds normal limits. So while the brightness illusion helps, it doesn't solve all problems. It trades one mystery for another. Either galaxies formed impossibly fast, or black holes grew impossibly fast. Reality probably involves some of both. Dust changes everything. Tiny grains of carbon and silicate, scattered through interstellar space, can fool even the most sophisticated telescopes into seeing the universe wrong. Here's how the trap works. When we measure a distant galaxy's age, we use its redshift, the amount by which cosmic expansion has stretched its light toward longer, redder wavelengths. Greater redshift means greater distance and earlier time. A galaxy at redshift 7 existed when the universe was 700 million years old. A galaxy at redshift 10 existed at 400 million years. The calculation seems straightforward. Measure the redshift, look up the corresponding time in standard cosmological tables, and determine when the galaxy existed. Except dust interferes. Dust grains absorb blue and ultraviolet light more efficiently than red light. When starlight passes through dusty regions, either within the galaxy itself or in intervening space, it emerges redder than it started. This process, called dust reddening, happens completely independently of cosmological redshift. If a galaxy at moderate distance has substantial dust, its light will appear redder than a clean, dust-free galaxy at the same distance. Measure this reddened light and you might conclude the galaxy is farther away than it actually is. You think you're seeing an ancient object when you're really seeing a younger, dustier one. This error would make galaxies appear older, more distant, and more extreme than they truly are. The impossible early massive galaxies might not be so early or so massive after all. Scientists are aware of this possibility. They've developed techniques to detect and correct for dust reddening. Different wavelength combinations respond to dust in predictable ways. By comparing measurements at multiple wavelengths, astronomers can estimate how much dust is present and compensate. But the techniques aren't perfect, especially for very distant galaxies where measurements have larger uncertainties. A galaxy that appears to be at redshift 7 might actually be at redshift 5 if dust has substantially reddened its light. That would place it 1 billion years later in cosmic history, plenty of time for it to grow massive without violating cosmological models. Some researchers think dust contamination explains a significant fraction of the apparent early massive galaxies. These objects might be younger, dusty galaxies, masquerading as ancient giants. The spectroscopy helps resolve this ambiguity. Dust affects different wavelengths in characteristic ways. It dims blue light more than red light. It creates a smooth, gradual reddening across the spectrum. In contrast, cosmological redshift shifts specific spectral lines to different wavelengths without changing their relative strengths. By examining the detailed spectral features, astronomers can distinguish dust reddening from cosmological redshift. If a galaxy shows spectral lines at the expected positions for redshift 7, and those lines display the right relative intensities, dust is probably not fooling us. The galaxy is genuinely at redshift 7. Most of the spectroscopically confirmed early massive galaxies pass this test. Their redshifts appear secure. They really do exist in the early universe. However, a few objects remain ambiguous. Their spectra are noisy or incomplete. Dust could be affecting them more than currently estimated. These questionable cases will require additional follow-up observations to settle definitively. The dust redshift trap represents another way observations might be fooling us. It's less dramatic than the brightness illusion from black holes, but potentially affecting more objects at a subtler level. Small, systematic errors in dust correction could add up, making the population of early massive galaxies appear somewhat larger than it truly is. Every possible source of error must be examined carefully. The stakes are too high to rush to conclusions. Something kills galaxies in their youth. We've found the bodies scattered across the early universe, but the murder weapon remains elusive. Normal galaxies in the modern cosmos form stars steadily for billions of years. They convert gas into stars at a moderate pace, occasionally spiking during mergers or collisions, but generally maintaining a long, slow burn. When they finally die, it's a gradual fade rather than an abrupt cutoff. Early quiescent galaxies are different. They blazed brilliantly for perhaps a few 100 million years, then shut down completely. The star formation didn't slow gradually. It stopped, like someone flipping a switch. What could flip that switch? In modern galaxies, several processes can halt star formation. Let's examine each and see if they work in the early universe. First, supernova feedback. When massive stars die, they explode violently, blasting their outer layers into space at thousands of miles per second. These shockwaves heat surrounding gas to millions of degrees. Hot gas cannot collapse to form new stars. If enough supernovae detonate in quick succession, they can heat all the gas in a small galaxy, preventing further star formation. This mechanism works for small galaxies today, but the early massive galaxies weren't small. They contained enough mass that simple supernova heating shouldn't have been enough to halt all star formation. Some regions should have remained cool and continued forming stars. Second, stellar winds. Even before dying in supernova explosions, massive stars produce powerful winds that push gas away from star-forming regions. In a galaxy undergoing intense star formation, with millions of massive stars all producing winds simultaneously, the cumulative effect could be substantial. But again, this process alone seems insufficient to explain the abrupt, complete shutdown observed in early quiescent galaxies. Stellar winds should slow star formation, not stop it entirely. Third, black hole feedback. This mechanism looks more promising. Supermassive black holes at galactic centers can generate incredible energy when they feed. Matter falling toward the black hole forms an accretion disk where friction heats the gas to extreme temperatures. This hot gas radiates intensely, creating pressure that pushes against additional infalling matter. Some of this energy escapes as winds moving at significant fractions of light speed. These winds can sweep through the entire galaxy, pushing gas out into intergalactic space. If the black hole is powerful enough and the galaxy compact enough, this feedback can remove essentially all star-forming gas in one catastrophic purge. This might explain the early quiescent galaxies. Perhaps they formed supermassive black holes early in their development. The black holes fed voraciously on available gas, grew rapidly, and then blew away the remaining fuel for star formation. The timing could work. A galaxy forming stars intensely for a few 100 million years would funnel large amounts of gas toward its center. This gas would feed a central black hole, allowing it to grow quickly. Once the black hole reached a critical mass, its feedback would become powerful enough to halt the process that created it. Fourth, environmental effects. In the modern universe, galaxies in dense clusters often become quiescent because surrounding galaxies strip away their gas. But this explanation fails for early quiescent galaxies because galaxy clusters hadn't formed yet. The universe was less than 1 billion years old. Dense environments didn't exist. Fifth, rapid gas consumption combined with lack of resupply. Perhaps these galaxies simply used up their available gas extremely quickly through efficient star formation and then couldn't acquire more. If they formed in isolated regions without nearby gas reservoirs, they might naturally starve themselves. This last possibility has appeal. It doesn't require exotic physics or extreme feedback. It just requires that some early galaxies formed in particularly isolated or gas-poor environments. The truth probably involves a combination of mechanisms. Black hole feedback, assisted by stellar winds and supernovae, operating on galaxies that formed with limited gas reservoirs. Multiple factors conspiring to shut down star formation permanently, but we still don't understand the details. Why these galaxies and not others? Why so early? Why so completely? Time is the ultimate constraint. Give the universe enough time, and almost anything becomes possible. Galaxies can grow, stars can form, structures can emerge. But what if you don't have enough time? The early massive galaxies accomplished in 500 to 700 million years what should require several billion years. They compressed multiple epochs of galactic evolution into a cosmic eye blink. Understanding how requires confronting what limits galactic growth. First limit, the speed of light. Nothing can travel faster. This constrains how quickly matter can come together. Even if gravity pulls forcefully, material can only fall toward a collapsing region at speeds less than light speed. For a galaxy-sized object, gathering enough matter takes millions of years minimum. Second limit, cooling time. Hot gas won't collapse. It must radiate away its thermal energy before gravity can pull it together. This cooling happens at rates determined by atomic physics, how quickly atoms can emit photons and carry away energy. You can't speed up atomic physics. Third limit, star formation timescales. Once gas clouds become dense enough, they fragment into stars. But this process isn't instantaneous. Turbulence in the gas, magnetic fields threading through it, and rotation all slow the collapse. Observations of modern star-forming regions show the process takes several million years. Fourth limit, feedback delay. Stars don't affect their surroundings immediately. A massive star forms, spends several million years on the main sequence, then explodes as a supernova. Only then does its energy impact the galaxy. This delay means feedback can't prevent the formation of the next generation of stars. Given all these limits, cosmologists calculated that galaxy formation should proceed gradually. Small proto-galaxies first. These merge to form larger galaxies. More mergers create spirals like the Milky Way. Eventually, massive ellipticals emerge from multiple spiral mergers. Each step requires time. The entire process, from first stars to mature massive galaxy, needs several billion years. Except it doesn't. The early massive galaxies prove the timeline can be compressed. Several proposed mechanisms might explain this compression. First, extremely efficient gas collapse in the early universe. Perhaps the first gas clouds were fundamentally different from modern ones. Lacking heavy elements like carbon and oxygen, they cooled through pure hydrogen processes. Paradoxically, this might have made them more susceptible to rapid, catastrophic collapse once conditions were right. Second, higher gas densities. The early universe was smaller and denser than today. For a given mass of material, densities were higher. Higher density means stronger gravity, faster collapse, and quicker structure formation. This doesn't eliminate the time requirements entirely, but it shortens them. Third, enhanced accretion rates. Modern galaxies grow partly by accreting gas from their surroundings. This process is slow because the gas must shed angular momentum, it's rotating, and must slow its spin to fall inward. Perhaps in the early universe, special circumstances allowed faster accretion. Fourth, primordial massive stars. If the first stars were much more massive than modern stars, hundreds of solar masses instead of tens, they would have lived shorter lives but produced more feedback per unit time. A galaxy dominated by these monsters would evolve faster. Fifth, early dark matter halo collapse. If dark matter halos formed faster than current models predict, they would provide gravitational wells for normal matter earlier. Galaxies could start forming sooner, giving them additional time to grow. None of these mechanisms alone seems sufficient, but in combination, with several effects reinforcing each other, they might compress billions of years into hundreds of millions. Testing these ideas requires understanding conditions in the very early universe better than we currently do. We need more observations of high redshift galaxies. We need more detailed spectroscopy revealing their gas content, star formation histories, and chemical compositions. Most importantly, we need to find the earliest galaxies of all those forming at 400, 300, perhaps 200 million years after the Big Bang. Webb is searching for these objects now. Each discovery will provide another constraint on how fast galaxy formation can proceed. The missing billion years represents the core mystery. Account for those years, explain how galaxies can form that much faster than thought possible, and the other puzzles start resolving. The path forward requires squeezing physics harder, finding overlooked mechanisms, and perhaps accepting that the early universe operated under slightly different rules than the present day. Time remains the ultimate test of any theory. The universe gives us a clock, and galaxies either meet it or they don't. Energy flows through the universe in cycles. Stars form from gas. Stars release energy. That energy affects the gas. The cycle continues. But with each turn, something changes. Feedback mechanisms control how galaxies grow. Without feedback, every bit of gas in the universe would have collapsed into stars billions of years ago. We'd live in a cosmos packed with massive galaxies, blazing with stellar light from edge to edge. Instead, we see a universe where most gas remains diffuse, scattered through intergalactic space. Feedback prevents runaway star formation. It's the brake pedal on galactic growth. 3 main types exist, and each operates differently. Stellar feedback begins when massive stars ignite. These giants burn so hot they emit intense ultraviolet radiation. This radiation ionizes surrounding gas, stripping electrons from atoms and heating the material to tens of thousands of degrees. Hot ionized gas has pressure. Pressure resists compression. Regions that might have collapsed to form additional stars remain puffed up instead. When the massive star dies, stellar feedback escalates dramatically. The supernova explosion releases as much energy in a few seconds as our own star will emit in its entire 10 billion year lifetime. This energy blasts outward at 10,000 miles per second, creating a shockwave that tears through the surrounding gas. One supernova can heat and disperse gas across hundreds of light years. A cluster of massive stars dying in sequence can impact an entire galaxy. Small dwarf galaxies can have their gas completely ejected into intergalactic space, permanently ending star formation. Black hole feedback operates on larger scales. When a supermassive black hole feeds, it doesn't consume matter quietly. The infalling material forms a swirling disk where friction heats the gas to millions of degrees. At these temperatures, the gas emits powerful radiation across all wavelengths. This radiation creates pressure, pushing against additional infalling material. Some of the gas never reaches the black hole. Instead, it gets accelerated outward in high-velocity winds. These winds can achieve speeds approaching 10% of light speed. A powerful active black hole can generate winds carrying more energy than all the supernovae in its host galaxy combined. These winds sweep outward, colliding with the galaxy's gas and driving it away. Observations of nearby active galaxies show these winds in action, creating cavities in the surrounding medium hundreds of thousands of light years across. Thermal feedback represents a third mechanism. Even without violent explosions or black hole winds, stars heat their surroundings simply by existing. The cumulative radiation from billions of stars can raise the temperature of galactic gas significantly. Warmer gas is more resistant to gravitational collapse, slowing the rate at which new stars form. In the early universe, these feedback mechanisms faced different conditions. Gas densities were higher, galaxies were more compact, distances between stars were shorter. Under these circumstances, feedback could be either more or less effective than today. More effective because the higher densities meant stellar winds and supernova shockwaves encountered more material. Each feedback event affected a larger mass of gas. Less effective because the stronger gravity in compact, dense systems could overpower even intense feedback. Gas blown away from star-forming regions might fall back within a few million years, ready to form stars again. Which effect dominated remains unclear. Computer simulations produce different results depending on exactly how feedback is implemented. Small changes in assumptions lead to large changes in predicted galaxy properties. The early quiescent galaxies provide a crucial test. These objects experienced feedback powerful enough to permanently halt star formation. Whatever mechanisms operated in them worked completely. No gas reserves remained. No recovery occurred. Explaining their abrupt death requires understanding feedback at its most extreme. Light tells stories. You just need to know how to read it. Every dead galaxy carries a signature in its spectrum, a sharp, unmistakable drop in brightness at a specific wavelength. Astronomers call it the Balmer break, and it's the forensic evidence proving when star formation ceased. Here's why it exists. Stars come in different colors depending on their temperature. Hot, massive stars glow blue-white, radiating intensely at short wavelengths. Cool, smaller stars glow red, emitting mostly at longer wavelengths. A galaxy's overall color depends on which type dominates. Young galaxies forming stars actively contain many massive hot stars. These blue giants contribute disproportionately to the galaxy's total light output, even though they're rare compared to smaller stars. Each one shines so brightly that relatively few can make an entire galaxy appear blue. But massive stars die quickly. Stars 100 times more massive than our own star burn through their fuel in just a few million years. When they die in supernova explosions, they vanish from the galaxy's light budget. The next most massive stars also live fast and die young. Stars 20 times more massive than our own last perhaps 10 million years. Then they're gone. As a galaxy ages without forming new stars, the massive, short-lived stars progressively disappear. First, the most massive, then the moderately massive. Eventually, after about 100 million years, only stars smaller than a few times our star's mass remain. This changing population creates a distinctive pattern in the galaxy's spectrum. The specific wavelengths emitted by hydrogen atoms in stellar atmospheres mark the boundary. Below a certain wavelength, light from hot stars dominates. Above it, cooler stars contribute more. When the hot stars die off, the galaxy's light below this boundary drops sharply. That's the Balmer break, a cliff in the spectrum revealing that the galaxy stopped forming massive stars long enough ago for them all to die. The break's strength indicates how long ago star formation ceased. A subtle break suggests star formation ended recently, some massive stars remain. A deep break indicates star formation ended long ago, all massive stars are gone, leaving only small red stars. RUBIESUDSQGZ7 shows a deep Balmer break. Its spectrum drops dramatically at the critical wavelength. This proves its stars are old. Star formation didn't just slow down, it stopped completely, long enough for every massive star to die. The spectrum reveals additional information. Absorption lines from calcium and iron appear, created by these elements in stellar atmospheres, absorbing specific wavelengths of light. The pattern of these absorption lines provides a fingerprint of the stellar population. Old stars show strong absorption from ionized calcium. Young stars show weaker calcium absorption, but strong hydrogen lines from their hot atmospheres. By comparing the relative strengths of different absorption features, astronomers can determine not just whether a galaxy is old, but exactly how old. For RUBIESUDSQGZ7, the analysis suggests star formation ended approximately 50 to 100 million years before Webb observed it. The galaxy formed, lived intensely for perhaps a few 100 million years, then went silent. Crucially, the spectrum shows no emission lines. When gas in galaxies gets heated by young stars or active black holes, it emits light at specific wavelengths, creating bright spikes in the spectrum. Star-forming galaxies show strong hydrogen emission. Active galactic nuclei show broad, intense emission lines. RUBIESUDSQGZ7 shows neither. No emission, just absorption. This confirms the galaxy is genuinely dead, not just dust obscured or dominated by a black hole. The Balmer break cannot be faked. Dust can redden a galaxy's light. Black holes can outshine stellar populations. But nothing mimics the specific pattern of a deep Balmer break, combined with old star absorption lines and absent emission features. It's the smoking gun proving these galaxies really are ancient corpses, frozen in time, defying every prediction about when galaxies should die. For decades, one idea dominated our understanding of how galaxies grow: the hierarchical model. Start small, merge, get bigger, merge again, repeat for billions of years. It made perfect sense. Dark matter clumps together gradually, forming small halos first. Galaxies form in these halos. The halos merge, bringing their galaxies together. Two small galaxies combine into one medium galaxy. Medium galaxies collide to create large spirals. Multiple spirals crash together to produce massive ellipticals. Bottom-up construction, like building a house brick by brick. Simple, elegant, testable. The model worked brilliantly for the local universe. When astronomers observed nearby galaxies, they found evidence of this hierarchical growth everywhere. Streams of stars torn from smaller galaxies during mergers. Dwarf galaxies orbiting larger ones, waiting to be consumed. Elliptical galaxies with properties suggesting they formed from spiral mergers. Computer simulations based on hierarchical assembly reproduced the observed universe remarkably well. Run a simulation forward for 13 billion years using this model, and you get galaxies with masses, sizes, and distributions matching what telescopes observe, until you run the simulation forward for only 700 million years. At that early time, the hierarchical model predicts that only small proto-galaxies should exist. Dark matter halos haven't had time to grow large. The mergers needed to build massive galaxies haven't occurred yet. You might find objects containing millions or tens of millions of solar masses, perhaps a few rare specimens reaching 100 million. You don't find galaxies containing 10 billion solar masses. The math doesn't allow it. The time is insufficient. Yet there they are. Multiple examples, confirmed spectroscopically, massive, mature, and ancient. The hierarchical model faces its most serious challenge. Either the model is wrong, or something critical is missing from it. Several modifications have been proposed. Perhaps the first dark matter halos formed faster than current simulations predict. If density fluctuations in the very early universe were larger than assumed, halos could have collapsed earlier. This would give galaxies a head start, allowing them to grow massive before the hierarchical model expected. But this modification requires adjusting initial conditions in ways that affect other predictions. The cosmic microwave background provides strong constraints on early density fluctuations. Any increase large enough to fix the galaxy problem creates new problems elsewhere. Another possibility involves changing how efficiently gas turns into stars during the earliest phases. Perhaps the first generation of galaxies converted gas to stars far more efficiently than later generations. This would allow small halos to build massive stellar populations quickly, bypassing the need for multiple mergers. This seems more promising. Physics in the early universe might genuinely have been different. Pure hydrogen and helium gas, never before processed through stars, could behave differently than metal-enriched gas. The high densities in the early universe might have promoted more efficient collapse. But how much more efficient? Enough to explain galaxies that formed 100 times faster than expected? That requires something approaching perfect efficiency, which brings its own theoretical challenges. A third modification questions whether galaxy mergers really proceeded as slowly as the hierarchical model assumes. Perhaps in the dense early universe, mergers happened more frequently. Perhaps proto-galaxies formed closer together, allowing rapid successive mergers that built massive galaxies quickly. Simulations exploring this possibility show some promise. Increasing the merger rate can produce more massive early galaxies, but it also produces side effects, more disturbed galaxy morphologies, different gas fractions that don't match observations. Every attempted fix creates new tensions. Solve one problem, generate others. The hierarchical model isn't obviously wrong, it's just incomplete. Something happened in the early universe that the current model doesn't capture. Some process, some mechanism, some difference in conditions that allowed galaxies to assemble faster than the simple bottom-up picture predicts. Finding that missing piece is now one of cosmology's highest priorities. Because if galaxies can form this quickly, what else have we misunderstood about cosmic evolution? Imagine a cosmic feeding frenzy. Small galaxies swarm together, pulled by gravity into an increasingly dense cluster. They collide, they merge, they devour each other in rapid succession. Could this process build a massive galaxy in a fraction of the expected time? The idea has appeal. Hierarchical galaxy formation happens through mergers, just spread out over billions of years. If somehow those mergers could be compressed into a few 100 million years, massive galaxies could form early without requiring new physics. All you need is the right starting conditions. Many small proto-galaxies forming close together. In the modern universe, galaxy mergers are relatively rare. Galaxies are spread out, separated by millions of light-years of empty space. When two galaxies do collide, it's a spectacular event, happening perhaps once every few billion years for any given galaxy. But the early universe was different, denser, more compact, the same amount of matter squeezed into a smaller volume. Under these conditions, proto-galaxies would have formed much closer together than their modern counterparts. Closer spacing means more frequent encounters. More encounters mean more mergers. A proto-galaxy in the dense, early universe might experience multiple mergers within a few 100 million years, each one adding mass and triggering bursts of star formation. Computer simulations testing this scenario show interesting results. Start with a region containing dozens of small proto-galaxies, each with a few 100 million solar masses. Let them interact gravitationally. Watch what happens. The most massive proto-galaxy attracts others through gravity. They fall toward it. Collisions occur. With each merger, the central galaxy grows. The added mass increases its gravitational pull, attracting more victims. A positive feedback loop develops. Within simulation time equivalent to 500 million years, the central galaxy can reach 10 billion solar masses, not through slow accumulation of gas, but through rapid consumption of neighbors. The simulations match several observed features of early massive galaxies. Their compact, successive mergers haven't had time to puff them up. They show high star formation rates during the merger process, and they can shut down abruptly when the supply of nearby victims runs out. But the scenario requires special circumstances. The proto-galaxies must form in an unusually dense region. If they're too spread out, mergers happen too slowly. If they're too close, they merge before individual galaxies can form much mass. Additionally, each merger generates turbulence and heats gas, potentially disrupting star formation. The process needs to build stars faster than mergers destroy star-forming regions. This balance is delicate. Observations provide some supporting evidence. Webb has discovered at least one system, nicknamed JWST's quintet, showing 5 galaxies merging simultaneously just 800 million years after the Big Bang. This system contains 17 distinct clumps of stars and gas, all interacting gravitationally. The total stellar mass of JWST's quintet approaches 10 billion solar masses. Researchers studying it suggest this merger will eventually produce a massive quiescent galaxy. The star formation might already be slowing as feedback from the violent interactions heats and disperses gas. If this single observed merger is typical, then perhaps many massive early galaxies formed through similar processes. Multiple smaller galaxies crashing together in quick succession, building mass rapidly before feedback shuts everything down. However, JWST's quintet is described as exceptionally rare. Finding 5 galaxies merging simultaneously is unusual even in the early universe. If all massive early galaxies required such rare events, we wouldn't see as many as observations suggest. The dwarf galaxy cannibalism scenario works sometimes, in special regions where conditions align, but it probably can't explain every massive early galaxy. Something else must contribute. Perhaps a combination of mechanisms operates. Efficient mergers in some regions, unusually efficient star formation in others, and primordial massive halos providing a head start in a few locations. The universe doesn't need one explanation. It might need several, each contributing to the population of mysterious massive early galaxies. 800 million years after the Big Bang, 5 galaxies met their doom. They converged, attracted by mutual gravity, and began a collision that will last millions of years. Astronomers found them frozen mid-crash, captured in Webb's infrared images. The system has a nickname, JWST's Quintet. Galaxy collisions aren't rare in the modern universe. We've observed thousands. The Milky Way is currently colliding with several smaller galaxies, slowly tearing them apart and absorbing their stars. In a few billion years, we'll collide with Andromeda in a spectacular merger that will reshape both galaxies. But 5 galaxies colliding simultaneously? That's extraordinarily rare. The Quintet system contains more than just the 5 main galaxies. 17 distinct clumps of stars and gas appear in the images, each gravitationally bound but distinct. Some are probably fragments torn from the main galaxies during the collision. Others might be proto-galaxies that haven't finished forming. The total mass exceeds 10 billion solar masses, distributed across the merger region, gravitationally interacting, triggering intense star formation where gas clouds collide and compress. Christopher Consolis, the astronomer who led the study, emphasized how unusual this discovery is. Finding a system with 5 physically linked galaxies is exceptionally rare, both in current simulations and observations. Galaxy mergers drive evolution. When galaxies collide, their gas clouds slam together, compressing and heating. Regions dense enough to resist this heating collapse rapidly, forming stars in massive bursts. The collision can trigger star formation rates hundreds of times higher than normal, but mergers also destroy. Tidal forces, differences in gravity's strength across an object tear galaxies apart. Stars get flung into intergalactic space. Gas gets heated and dispersed. The delicate structures that support steady star formation shatter. Whether a merger creates more stars or ends star formation depends on the details. The masses involved, the collision speed, the angle of impact, the gas content. Small variations produce dramatically different outcomes. For JWST's Quintet, the outcome remains uncertain. The system shows high star formation rates now, with gas compressed by the collisions igniting new stars throughout the merger region. But this can't continue forever. As the merger progresses, the galaxies will sink toward a common center, pulled together by gravity and slowed by friction. Eventually, they'll coalesce into a single object. If star formation continues through this process, the result will be a massive, star-rich galaxy. But if feedback mechanisms activate, if supernova explosions and stellar winds heat the gas enough, or if a central supermassive black hole forms and begins ejecting material, star formation could shut down abruptly. The merger would create a massive quiescent galaxy, dead before its first billion years. This second scenario interests researchers because it might explain some of the early dead galaxies. If quintet-like mergers were more common in the dense early universe, they could rapidly build massive galaxies and then kill them through extreme feedback. The system offers a preview of a process happening in real time. Observations over the coming years will reveal whether star formation continues, slows, or stops. Webb can track changes in the infrared light, monitor the star formation rate, and watch the merger evolve. However, the rarity of such systems remains problematic. If massive early galaxies mostly formed through quintet-like mergers, we should see many more merger systems than we do. The early universe wasn't that much denser. Perhaps quintet mergers represent one extreme pathway. Most massive galaxies formed through less spectacular processes, binary or triple mergers rather than quintuples. But the quintet shows what's possible when circumstances align perfectly. Nature experiments with galaxy formation constantly, trying different combinations, different initial conditions, different merger configurations. Most experiments produce ordinary results, but sometimes conditions conspire to create something extraordinary. JWST's Quintet is one of those extraordinary experiments, preserved in light for us to study. Everything you touch, everything you see, everything made of atoms. Scientists call it baryonic matter, protons and neutrons, The particles in atomic nuclei are baryons. Baryonic matter is the normal stuff, distinct from dark matter and dark energy. But in the early universe, even normal matter was scarce. After the Big Bang, the cosmos contained a specific fraction of baryonic matter relative to dark matter. This ratio is set by nuclear physics in the first few minutes of cosmic history and has remained constant ever since. Approximately 15% of all matter is baryonic. The rest is dark matter. That 15% sounds like plenty. Surely enough to build galaxies, right? The problem is distribution. Most baryonic matter doesn't live in galaxies. It exists in a diffuse form, spread through intergalactic space. This warm, hot intergalactic medium contains perhaps half of all baryonic matter. Another significant fraction remains in even more diffuse form, never having collapsed into any structure. Only about 10% of baryonic matter actually ends up in galaxies. The rest remains scattered. This creates severe constraints on early galaxy formation. Not only is there limited time for galaxies to grow, there's limited material available. The massive early galaxies would need to collect a disproportionate share of nearby baryonic matter. Think of it like this. Imagine a desert with water hidden underground. You need to collect enough water to fill a swimming pool, but you can only drill in one small area. Most water is too far away to reach. You're limited to what's directly accessible. The massive early galaxies faced this problem. They needed to gather billions of solar masses of baryonic matter from their immediate surroundings. But calculations suggest not enough matter existed in their vicinity. This is where dark matter halos become crucial. Dark matter provides the gravitational wells that attract baryonic matter. A galaxy can gather baryonic matter from an area much larger than the galaxy itself because the dark matter halo extends far beyond the visible galaxy. In the modern universe, this works efficiently. Large dark matter halos have had billions of years to pull in baryonic matter from wide regions. Galaxies grow slowly as their halos accumulate material. But in the early universe, dark matter halos were still forming. They hadn't had time to grow large. Their gravitational reach was limited. They couldn't pull in baryonic matter from as wide an area. Additionally, much of the baryonic matter in the early universe was still hot from the Big Bang. Hot gas has pressure. Pressure resists gravitational collapse. For baryonic matter to fall into dark matter halos and form galaxies, it must cool enough that gravity overcomes pressure. Cooling takes time. In the early universe, this becomes another rate-limiting factor. The baryonic matter exists. The dark matter halos exist. But the matter isn't cold enough to collapse into the halos quickly. Some researchers have proposed that perhaps more baryonic matter was available in special regions. If the universe wasn't perfectly uniform, if some areas had higher baryonic to dark matter ratios than average, those regions could form massive galaxies more easily. But this violates what we know about the early universe's uniformity. Observations of the cosmic microwave background show that density variations were tiny, less than 1 part in 100,000. Such small variations shouldn't produce regions with dramatically different baryonic content. Another possibility involves more efficient gathering. Perhaps baryonic matter fell into early dark matter halos more readily than models predict. Perhaps the hot gas cooled faster. Perhaps gravitational effects were stronger. Each possibility requires checking against other observations. You can't arbitrarily adjust one parameter without affecting everything else. The baryonic matter mystery represents a fundamental budget problem. The universe has a fixed amount of normal matter available. Building massive galaxies requires collecting a large fraction of that matter into small regions. The early universe had less time and weaker gravitational wells to accomplish this gathering. Yet somehow, it happened. The massive galaxies exist. They found the baryonic matter somewhere. Understanding where it came from and how it assembled so quickly remains one of the central puzzles. Dark matter shapes the universe, but we don't know what it is. For decades, scientists assumed it was cold, made of slow-moving particles that clump together under gravity. This assumption worked well, until maybe it didn't. Cold dark matter creates specific patterns when it collapses into structures. Simulations show it forming nearly spherical halos. These halos start small and grow through mergers. The process is gradual, orderly, predictable. Galaxies forming in cold dark matter halos should follow a particular timeline. Small galaxies first, within a few 100 million years. Larger galaxies later, after billions of years of mergers. The massive early galaxies violate this timeline. What if dark matter isn't cold? What if it has different properties? Two alternatives have gained attention: warm dark matter and fuzzy dark matter. Each behaves differently from cold dark matter, potentially allowing faster structure formation. Warm dark matter consists of particles moving at significant fractions of light speed. This speed prevents warm dark matter from clumping on small scales. It smooths out the smallest density fluctuations, suppressing the formation of dwarf galaxies while still allowing larger structures. In a warm dark matter universe, the first structures to form might be larger than in a cold dark matter universe. Instead of countless tiny halos merging slowly into bigger ones, you'd get fewer but more massive halos forming directly. This could accelerate the creation of massive galaxies. However, warm dark matter also has problems. It predicts fewer dwarf galaxies than we observe. The same mechanism that prevents small-scale clumping should eliminate most dwarf galaxies, yet we see many in the local universe. Reconciling these observations with warm dark matter has proven difficult. Fuzzy dark matter offers a different twist. Instead of classical particles, fuzzy dark matter consists of ultralight particles that behave quantum mechanically. These particles have wave properties. When many fuzzy dark matter particles occupy the same region, they create interference patterns, like ripples on a pond. Simulations of galaxy formation in a fuzzy dark matter universe produce striking results. Instead of spherical halos, fuzzy dark matter forms elongated filaments. These filaments are striated, showing wave-like patterns. Galaxies would form along these filaments rather than in isolated spheres. Mark Vogelsberger, who led simulations of fuzzy dark matter, described the early universe in this scenario as looking like starlit strings on a harp. The galaxies would stretch out along filamentary structures, giving the cosmic web a more pronounced appearance. Formation along filaments might proceed faster than formation in spheres. Filaments channel matter efficiently, bringing gas and dark matter together along preferred paths. This could explain how some galaxies grew massive so quickly. But fuzzy dark matter faces its own challenges. The particle mass must be extremely small, about 22 orders of magnitude lighter than an electron. At this mass, quantum effects operate on galaxy-sized scales, creating observable consequences. Those consequences should appear in the cosmic microwave background and in the distribution of large-scale structure. So far, observations haven't clearly detected them. The data remain consistent with cold, dark matter. Future telescopes might distinguish between these scenarios by observing the very first galaxies. If dark matter is cold, early galaxies should form in compact, roughly spherical halos. If it's warm, the smallest galaxies should be missing. If it's fuzzy, galaxies should show preferential formation along filaments with characteristic wave patterns. Webb is beginning to gather this evidence. Each new deep field image reveals more about galaxy distribution patterns in the early universe. Are they randomly scattered or aligned along filaments? Are small galaxies as common as cold dark matter predicts? The answers will reveal something fundamental about the invisible matter that comprises most of the universe's mass, and possibly explain how impossible galaxies became possible. The universe has structure, not the random scattering you might expect from an explosion, but an organized pattern stretching across billions of light years. Astronomers call it the cosmic web. Filaments of dark matter and gas stretch between galaxy clusters, forming sheets and walls. Between these structures lie vast voids, empty regions where almost nothing exists. The pattern resembles a three-dimensional spider web. or the foam in a bubble bath. This web formed through gravity's patient work. Tiny density fluctuations in the early universe regions, slightly denser or less dense than average, grew over time. Gravity pulled matter toward denser regions. As these regions grew, their gravity strengthened, pulling in more matter. A feedback loop developed. The result: matter flows along paths of least resistance, following gravitational gradients, accumulating in filaments and at filament intersections. The most massive galaxy clusters sit at these intersections, where multiple filaments meet. The cosmic web structure influences galaxy formation profoundly. A proto-galaxy forming in isolation, far from filaments, has limited access to fresh gas. It can form stars only from its initial supply. When that's exhausted, star formation stops. A proto-galaxy forming along a filament has constant access to inflowing gas. The filament channels material directly toward the galaxy. Star formation can continue for longer, sustained by this cosmic pipeline. In the early universe, the cosmic web was just beginning to form. The larger structures hadn't emerged yet, but the seeds existed regions where dark matter was slightly overdense, beginning to pull in surrounding material. Galaxies forming in these overdense regions would have had advantages. More available matter nearby, stronger gravitational fields accelerating collapse, more frequent mergers with neighbors, driving rapid mass growth. Perhaps the massive early galaxies simply formed in the right locations, not everywhere, but in those special regions where the nascent cosmic web was most pronounced. Simulations exploring this possibility show promise. Run a cosmological simulation including realistic cosmic web formation. Identify the densest knots where filaments are beginning to emerge. Zoom in on galaxies forming there. These privileged locations can produce galaxies significantly more massive than typical galaxies forming in average density regions. Not 100 times more massive, the cosmic web alone doesn't solve the entire problem, but 2 to 3 times more massive seems achievable. Combine this cosmic web boost with other effects: efficient star formation, rapid mergers, early dark matter halo collapse, and you might reach the observed masses. The filamentary structure also affects gas accretion rates. Gas flowing along filaments can reach galaxies faster than gas diffusing from random directions. It's like the difference between water flowing through a pipe versus soaking through soil. The pipe delivers far more water per unit time. Higher accretion rates mean more fuel for star formation. More fuel means potentially more stars forming per unit time. If early galaxies formed at filament intersections with multiple streams delivering gas, they could sustain intense star formation longer than isolated galaxies. This scenario predicts something testable. Massive early galaxies should be clustered. They should appear preferentially in the densest regions, where the cosmic web was forming most rapidly. Isolated massive galaxies far from overdense regions should be rare or absent. Webb's observations are beginning to test this prediction. Surveys mapping the three-dimensional distribution of early galaxies can reveal whether they cluster as the cosmic web scenario predicts. Initial results suggest some clustering, but the data remains limited. We need larger surveys covering more volume to draw firm conclusions. The cosmic web reminds us that galaxies don't form in isolation. They're embedded in a larger structure that channels matter, influences growth, and determines ultimate fates. Understanding galaxy formation requires understanding this web where it was thickest in the early universe, how quickly it assembled, and how efficiently it delivered material to growing galaxies. The impossible galaxies might just be the cosmic web's most successful early projects. 13 billion years ago, galaxies that shouldn't exist formed anyway. Today, we exist to puzzle over them. The connection matters more than it might seem. Every atom in your body formed in a star. Carbon, nitrogen, oxygen, calcium, iron, forged in stellar cores through nuclear fusion. When those stars died, they scattered these elements into space. Later generations of stars and planets formed from this enriched material. You are literally made of stardust. Not poetically, literally. But for you to exist, those first generations of stars needed to form. They needed to create heavy elements. They needed to die and disperse those elements. The process needed to happen efficiently enough that billions of years later, a rocky planet orbiting a medium-sized star could develop life. The massive early galaxies accelerate this timeline. If galaxies formed faster than we thought, they processed gas into stars faster. Stars created heavy elements faster. Those elements dispersed into the universe faster. This suggests the building blocks of life became available earlier in cosmic history than previously believed. Planets like Earth could have formed when the universe was younger. Life might have had more time to develop elsewhere, or perhaps not. If the massive early galaxies died quickly, becoming quiescent, they removed themselves from the cosmic chemical enrichment process. Their stars locked away heavy elements rather than returning them to space. This could slow the spread of life-enabling materials. The implications extend beyond astrobiology. They touch fundamental physics. If our current models of cosmology fail to predict galaxy formation correctly, what else might they mispredict? The models we use to understand cosmic expansion, dark energy, and the ultimate fate of the universe rest on the same physics as galaxy formation models. Cracks in one foundation raise questions about the whole structure. This doesn't mean everything is wrong. The standard model of cosmology works brilliantly for many phenomena. It predicted the cosmic microwave background's properties decades before we could measure them precisely. It explains the universe's large-scale structure. It accounts for the abundances of hydrogen and helium, but it's incomplete. The massive early galaxies prove this. Something happened that our models don't capture. Finding that missing piece will likely teach us something profound about the early universe. Perhaps about dark matter's true nature. Perhaps about how star formation proceeds under extreme conditions. Perhaps about forces or particles we haven't discovered yet. Each answer will expand our understanding of cosmic evolution and of our place in it. Consider the journey of knowledge. Centuries ago, we thought Earth was the center of everything. Then we learned we orbit a star. Then we learned our star is one of billions in a galaxy. Then we learned our galaxy is one of billions in the universe. Each revelation made us seem smaller, but it also made our story richer. Now we're learning that galaxies themselves have more complex histories than we imagined. They grew faster, lived harder, died younger. The universe was a more violent and dynamic place in its infancy than we realized. We're still here, 13 billion years later, because some chain of events survived that violence. Some galaxies lived long enough to enrich the cosmos with heavy elements. Some stars formed in quiet enough regions to host stable planetary systems. Some planets developed conditions suitable for life. Understanding the impossible galaxies helps us understand which paths led from chaos to order, from formless matter to complex life, from the Big Bang to conscious beings capable of looking back and asking why. The universe doesn't need to make sense to us. It simply is. But the fact that we can study it, puzzle over it, gradually uncover its mysteries, that's perhaps the most remarkable feature of cosmic evolution. 13 billion years after galaxies that shouldn't exist formed anyway, their light reaches us. We capture it with telescopes. We analyze it with computers. We debate its meaning. And slowly, piece by piece, we learn what the universe was trying to tell us all along. The impossible galaxies taught us humility. They reminded us that nature operates on principles we're still discovering. They showed us that confidence in our models must always be tempered with openness to surprise. Most importantly, they demonstrated that the universe still holds secrets, still has mysteries waiting, still offers discoveries that will challenge everything we thought we understood. The journey continues. Webb keeps observing. Scientists keep analyzing. Theories keep evolving. And somewhere out there, beyond the edge of the observable universe, in regions we'll never see, even stranger objects might exist, things that would make the impossible galaxies seem ordinary by comparison. The cosmos is vast, our knowledge is limited, but our curiosity is boundless. That's what the impossible galaxies ultimately mean for us. There's always more to discover, always deeper to look, always further to reach. The universe invites us to keep exploring, and we accept,